So now we're going to talk about alternating series. An alternating series is a series whose terms strictly alternate positive and negative. So you can't have a couple of positives and then a negative and then a positive and then a couple more negatives. It has to literally be positive, negative, positive, negative, positive, negative, positive, negative. Doesn't matter what it starts with, but it has to alternate. So here's some examples of how that might be expressed. The most common way of expressing it is having negative 1 to the n. Could also be negative 1 to the n minus 1 or whatever, depending on whether you want to start with a positive or a negative. And then n factorial here is just to generate some kind of a series. But negative 1 to the n, negative 1 to the first, negative 1 squared, negative 1 cubed, etc. Those are going to be negative, positive, negative, positive, negative, positive. Here's another one. It's not very common because we don't like to use I in series because sometimes I is the index. But in case you do, I, the imaginary number I to the 2n is going to alternate because I squared is negative 1, I to the 4th is positive 1, I to the 6th is negative 1, etc. So this would be an example of an alternating series. But you could also use trigonometry. Cosine of n pi, for example. Cosine of pi is negative 1. Cosine of 2 pi is positive 1. Cosine of 3 pi is negative 1. Cosine of 4 pi is positive 1, etc. So this can also alternate strictly. And then, of course, the 2 to the n there is just to create some kind of a series that's neither here nor there. It's this part that I wanted you to focus on in terms of the strictly alternating aspect. So let's talk now about the alternating series test. So if you have an alternating series, when will that alternating series converge? So what I'm going to do here is I'm listing in a vertical sense the y values essentially of the sum. S1 is the sum of the very first term, so it literally is equal to the very first term. S2 is the sum of the first term and the second term. Now, if A1 arbitrarily is a positive number, so let's say 0 is somewhere over here, we added A1, and then we're subtracting, because A2 is a negative number, that's how you get to S2, but then we're adding, because A3 is a positive number, to get to S3, but then we're subtracting to get to S4, then we're adding to get to S5, subtracting, adding, subtracting, adding, subtracting, adding, subtracting, adding, subtracting. You can see how if we follow this add, subtract pattern, there may be a way to have this converge to some limit somewhere along the way, or if you want to think of it as kind of like an asymptote. But in order for that to happen, a few things must be true. The first is that obviously the series must be strictly alternating. If it is not strictly alternating, then you might add a couple and then subtract, and now all of a sudden you're off the asymptote because now you're leading over here. And then you subtract a few times and then add, and then now you're over here. So it has to strictly be plus, minus, plus, minus, plus, minus, so that you're going up, going down, up, down, etc. Also, the absolute value of an plus 1 must be less than the absolute value of an. I'm using absolute value here because these are, one is going to be a positive number, one is going to be a negative number, so I'm just going to force them to both be positive. So in other words, that every time I add another thing on or subtract it, it was smaller than the one before it. So an plus 1, absolute value, less than an. So each time I'm going a shorter distance away from where I was before. So the up and down pieces are smaller every time. And also that if I went to infinity, that the individual terms would have to go to 0, because if they did not, let's say the limit of an went to 1, then ultimately I'm adding and subtracting about 1, plus 1, minus 1, plus 1, minus 1. What I want is to be essentially adding and subtracting almost 0, plus 0, minus 0, plus 0, minus 0. And that's how I'm going to get this limit. So these are the three things. The series itself has to be strictly alternating. The absolute value of an plus 1 must be less than the absolute value of an. After a certain point, it does not have to happen at the beginning, right? You can have weird swings at the beginning, but ultimately settle down. So after some k, just like with any series, we don't really care about what happens at the beginning in terms of convergence. It's toward the end of the series as n goes to infinity that we care. And then the limit as n goes to infinity of an has to equal 0. If those three things are true, then the series converges by the alternating series test. Now, if this were not true, we know that the test for divergence already says that the series would diverge. So this is essentially just making sure that the test for divergence does not create a divergent series, but it has to be there regardless. So we have to have these three things. All right, so now let's talk about the alternating series estimation. So as we did with the integral, if you want to estimate the sum of a series, of a convergent series, obviously, then you just essentially truncate after a while. You stop counting and you say, okay, now that's going to be my guess. And then the question is, how bad could my error be? What's an upper bound of how much error I might have? And if I can reduce that error, I can get a better and better approximation. So luckily, the alternating series error calculation is quite straightforward. So of course, in order to approximate the series to infinity, we stop after k terms. R sub k is called the error, and it literally means the remaining sum. But if you think about it, if I've done my series, remember these are all the xs, whatever value, the series values by adding, subtracting, and I've got to my sk, then here's the actual sum right there. That's the limit. Then ak plus 1 is either going to be going down or going up, but in this case I made it go down, is going to go past that limit. We know for sure because each time we go either above or below the limit, so that the next time we can come and cross it again and eventually settle. So the next term will definitely go past where the limit was. So the worst possible error is if you just look at the absolute value of whatever that next term is. So maybe that's the next term, and then after that, all the terms after that are 0. That would be the worst case scenario. In fact, we're pretty sure that the value of rk is less than ak plus 1. So we could just say less than if we wanted to. So here's our first example. We're going to show that this particular series over here converges. So I first noticed that -1 to the n is going to make this alternate. So I'm going to try the alternating series test. So I'm going to first say start by saying sigma n equals 1 to infinity of -1 to the n over n strictly alternates. That's the first thing I need to be able to say for the alternating series test. The second thing to say is a sub n plus 1 would be -1 to the n plus 1 over n plus 1, and a sub n would be -1 to the n over n. And if I do the absolute value of a sub n plus 1, well, that's just 1 over n plus 1, because the -1 to the n plus 1 part doesn't matter. And we know that is definitely less than 1 over n, because after all, this denominator is bigger than that denominator. But this 1 over n would just be the absolute value of the a sub n, which is over here. So we know that absolute value of a sub n plus 1 is less than absolute value of a sub n. So that's the second statement we needed. The first was strictly alternating. The second is that each term in absolute value sense is less than its previous term. And finally, if I do the limit as n goes to infinity of a sub n, well, that's just the limit as n goes to infinity of -1 to the n over n. Well, -1 to the n is going to be +1, -1, +1, -1, but the denominator here is going to go to infinity, so this limit is going to go to 0, which basically is a verification that the test for divergence doesn't create a divergent series. And so now I have all I needed, so I can say by the alternating series test, sigma n equals 1 to infinity of -1 to the n over n converges. Now this particular series, I did this as an example, but this particular series has a special name. It very much looks like the harmonic series 1 over n, but this is the alternating harmonic series, and since we've now shown that it converges, it's one of those like the P series or geometric series where very common, the alternate harmonic is very common, and so you can, in the future, simply state this is the alternating harmonic series and therefore it converges. unless, of course, you're asked specifically to prove that this series converges, in which case then the method is the alternating series test. All right, final example is to find the sum of this series correct to 3 decimal places. Well, first of all, I would verify it converges, but it will, so I'm going to skip that. So again, I'm going to truncate after a while, but I want to notice here that this is a convergent alternating series. Which means that the r sub k, the error, has to be less than the absolute value of a sub k plus 1. So, well, a sub k plus 1, or absolute value of that, would just be 1 over k plus 1 factorial. Of course, the negative 1 to the n minus 1, that part makes it strictly alternating, but I want the absolute value of it anyway, so that's just 1. And so k plus 1 factorial is the value from the denominator. Now this value has to be less than 0.0005. Again, same reason as before. If I can get it to be less than 0.0005, then with the rounding, when I go to that third decimal place, I can guarantee that my error is no larger than 0.001. And again, the error here is less than this value, which is then less than this value, so that guarantees the error is less than that value. Now, there's no easy way to solve this equation. I am going to write it a little differently. I'm going to say that k plus 1 factorial has to be greater than 2,000. That's by taking the reciprocal of the 0.0005, which is 1/2000th. And then the only good way to do this is to just plug in different values into the factorial. And I notice that 6 factorial is equal to 720, but 7 factorial is equal to 5,040. So what that means is that if I use k plus 1 equals 7, or in other words, k equals 6, then I have the inequality that I want, that k plus 1 factorial is greater than 2,000. There's no other way to do this other than guess and check. But luckily, you don't have to go very far generally to get your k. So we're going to use k equals 6. So now the question did not say how many terms are required. It actually wants that sum. So what we need to do is we need to say sigma n equals 1 to infinity of negative 1 to the n minus 1 over n factorial is approximately sigma n equals 1 to 6 of negative 1 to the n minus 1 over n factorial. And you could actually list out the different values if you want to, or you can let your calculator do the work. And here we get 0.631944. Now we know that the error is going to be less than 0.0005, which means if we do some rounding here, even then we'll be okay, because this allowed for the rounding to that third decimal place to still be with, not create any additional error that would take us away from the 3 decimal places of accuracy. So now I'm going to round this into 0.632, and I'm still convinced that this value here is correct to 3 decimal places for the entire sum.